Hi there, welcome back to the course on distributed systems. In the previous videos, we talked about how to construct asynchronous broadcast and asynchronous Byzantine agreement in a setting with strictly less than 1/3 corrupted parties. Now I'll try to convince you that that is the best we can do. Okay? So in particular, if we have 4 servers, we can at most tolerate that one of them crashes. That's what we know how to do. And I'll now try to convince you that it's also the best we can do. We're halfway done because we showed that in the synchronous model, if we only have authenticated channels, T strictly less than n3 is the best we can do. The asynchronous model is strictly worse for us than the synchronous one because it's just the synchronous one where we took away the clocks and we took away the guaranteed delivery times on messages. So clearly we cannot do better in this setting here. There's a little bit of a subtlety in that we changed the termination condition, but it's very easy to see that the same arguments apply here. So we're not going to dive into that. But could it be that with signatures, we could do broadcast and Byzantine agreement better than T less than n3? We certainly saw that in the synchronous case, signatures helps us quite a lot. We get 2.5 here, and we get to up to any number of corruptions here. We'll see that they don't help us. Okay. But here's the question I want to explore. So could we do better than this strictly smaller than n3? Could it be that we can tolerate, let's say, at least 3 T corruptions? So if one is T is 1, that means we could have 3 parties and tolerate that one of them crashes and still do, let's say, broadcast. We can't, and we're going to prove that now. It's important to prove such things, mostly because, of course, we don't want to look stupid. We don't want to come with a protocol and say, hey, here's a protocol that tolerates 1 crash server out of 4. And then our boss says, that sounds bad. Couldn't you tolerate like 1 out of 3 so I can save a server? And then we don't want to say, I don't know. We want to say, no, we can't. Should I tell you? And he'll probably be like, no, that's fine. But if you're sure, we're good. Now, of course, you're taking a course here, so you can't say, no, I'm going to tell you why it is. And more importantly, I mean, jokes aside, we want to know such lower bounds here for our own comfort. We want to stop looking for a protocol that works for the case 1 out of 3, right? So we know how to do 1 out of 4. Proving that we cannot do 1 out of 3 makes us feel good. We do the best we can. That's always the best we can hope to do. Okay. I'm going to prove it by contradiction. Okay. As we did earlier in the course, it's easy to show that if we can do it for n equals 3t, for any t, let's say 2, if we can do something that tolerates 2 out of 6 crashes, then we can also do something that tolerates 1 out of 3 crashes. We just group the servers in 2 and make those virtual parties. So each party in the 3-party protocol will be running 2 in the original one. And then it's doing the same thing, but now with 3 parties. And if I corrupt 1 virtual party, I corrupt 2 in the previous one. So if you could tolerate 2 out of 6, this virtual protocol can tolerate 1 out of 3. So to rule out 2 out of 6, it's enough to rule out 1 out of 3. Okay? We can pause and think a little bit about it. It goes in the right direction, right? Because if I could do 2 out of 6, then I can do 1 out of 3, and I know I can't do 1 out of 3, so I conclude I can't do 2 out of 6. Okay, so let's focus on the case with 3 servers. And then to add to the abstraction, I'm going to do a proof by contradiction. I'm going to assume I have such a protocol, and then I'm going to show something impossible. Okay. So first of all, what do we have to work with to try to reach our contradiction? I have a 3-party protocol. with agreement and validity. Agreement says, so let's say I'm looking at broadcast here. So let's make P1 the broadcast. I'm trying to send the same message to P2 and P3. And if P1 is corrupted, it shouldn't succeed in making them output different things. So by agreement, these two here will output the same thing. And actually not. Because by termination 1, we only know that if P1 is honest, is it guaranteed that they output something? It could be that they don't output something. But we know by termination 2 that if P2 does output something, then P3 eventually outputs the same. So that's what we have to work with. Okay. So from agreement, we know that either P2 and P3 output the same eventually, or they output nothing. They run forever. That's what we have from agreement. Validity, on the other hand, combined with termination 1, which says that when the sender is honest, parties do output something, says that if P1 outputs a 0, for example, then P2 will eventually output a 0. It also says that if P1 outputs, tries to send a 1, then P3 will eventually output a 1. Okay? That's what we have to work with. And I'm going to do one of these scenario proofs again, where I construct a really strange 4-party protocol, and then I make it do something impossible. So I'm going to take the sender, the honest sender, and make 2 copies of it. And just make 2 copies of that code. I run one of the pieces of code with a 0. So honestly try to send a 0. And this one is honestly trying to send a 1. Look at this as one corrupted party. So that's the adversarial strategy. And it doesn't let these 2 copies talk to each other. And then it lets the party trying to send a 0 talk to P2. Of course, now trying to make this one output a 0. And it makes this one here talk to P3, making it try to output a 1. And now, the last thing we're going to do, we're going to use the power that we are the adversary and that we're in an asynchronous model where the messages could be arbitrarily delayed and where I, now the adversary, controls that delay. So I will do an not infinite, but arbitrarily long delay here. Okay. In particular, I'll keep delaying this one until P2 makes an output. If it makes an output. So let's say in this setting here, if I made an infinite delay, P2 would at some point make an output, let's say after 10 hours, then I'm going to set the delay in the network to be 11 hours. Okay? So that's almost the same as having an infinite one, because let's say this, I know that in this setting, this guy here terminates after 20 hours. Well, I'm going to set the delay to be 21 hours. Okay? So that's the same as having infinite delay, because it just set this delay so long that it happens after the party is terminated and they can't do anything. They might see some messages afterward that make them realize, shit, I outputted the wrong message, I broke validity, but it's too late to take it back from the API. Okay, so let's just, for the sake of argument, put an infinite delay here. What will happen here? Will P2 output something? And if it outputs something, what will it output? And maybe this guy, does it output something? And if we're lucky, does it output something else? It does. So as we saw in these scenario proofs before, I can take this weird protocol here and then take different looks at it. But I'm only changing the look, my way to look at the protocol. I'm not changing the protocol. One look at it is that this party here is considered one corrupted P1. And I have very long delays here. Then I have a corrupted sender and 2 honest receivers. So I have validity. Okay? I have that if P2 and P3 output something, then they output the same thing. This already looks fishy, right? Because there's a line here across which there is no communication. P2 is talking to that thing, P3 is to that thing. Somehow they manage to output the same, if they output something. So well, if that should work, probably in this case, they don't output something, right? Now I'm going to show that that is not the case. Okay? Because I can also take this protocol and consider it as a corrupted P2. You see, if you take this here and consider it as one virtual party with some complicated behavior, then it's connected to P1 and P3 exactly as a P2 up here. So it has a dashed line here and a solid line here. So I could take this thing, package it, and run it inside of P2, and then this protocol would behave exactly like this protocol. So now there's only one corrupted receiver and an honest sender. So I have termination 1 and I have validity. So I know that P3 will output whatever the honest sender is sending, which is a 1. And there's termination 1 because the sender is honest. So I know in this situation, P3 will output a 1. Then I do the same over here. Say, no, you know what? I could take all this here and consider a corrupted P3. Full line, dotted line. There's a dotted line here, solid line here. So I could take all this machinery down here, package it into P3 and run it up here. Then we're in a setting with an honest sender, an honest receiver, and 1 corrupted party. And I assume a protocol can tolerate a corrupted party. So in this configuration here, P2 will output 0 because the honest sender is sending a 0. So I know in the setting, and by termination 1, because the sender is honest, I know it outputs something, and it outputs a 0. Okay? Then all in all now, I have concluded that in this 4-party protocol, P3 will output something, and it outputs a 1. P2 will output something, and it outputs a 0. And up here, I concluded that if they output something, they output the same thing. These 3 statements are obviously in contradiction with each other. Okay? So taking a more vague look at that argument, the argument would be something like this here. If you take P1 and you make it behave as if it's sending a 0 to that guy, as if it's sending a 1 to that guy, like over here, and delay the messages here, then there is no communication from that to that. Right? So obviously, the only way they could output the same is to not output something. But they're not allowed to do that because they're supposed to be able to tolerate a corrupted party. And if that one is talking to that one, and this one is not saying something, that could just be a crossed party. And in that case, P2 had to output something. So it's not allowed to not output something when it doesn't hear from P3. Well, that's bad because it could just be talking to P1, which could just be pretending to send a 0 to it. That's why 3 parties doesn't work. The 2 honest parties might not get time to compare notes, which they could in the synchronous model, because they would just wait long enough for this message here to arrive. That's why we lose quite a lot in the bounds. That's what there is to that argument. So that rules out broadcast with T des and N third. Okay. Then there's the Byzantine agreement. Could we get lucky here? And we can't. And the proof here is to some extent simpler. Let's say I could do this here with up to n half corruptions, okay? Then the way I would rule it out was to say, you know, if I can do this here, then I can also do broadcast. Therefore, if I could do better here, I could also do better broadcast. So that's what I will do. So to prove that this cannot be done better than up here, I just show that if I can do this, then I can also do broadcast without losing anything in how much corruption I tolerate. Okay. Actually do a little construction here in the middle of the impossibility proofs. So how would I do that? So what was it I needed to do? I needed to show that if I can do Byzantine agreement, then I can also do broadcast. That's the slide on it, but let's just talk our way out of it. So I can do Byzantine agreement, and I want to be able to do broadcast. Okay. So what I do, let's just say I want to broadcast a bit. Okay. If I want to broadcast a longer message, I can just broadcast it bit by bit. That's not efficient, but it works. Okay. So how do I broadcast a single bit? Well, I take the bit, and then I just send it to everybody. I just tell people what I would like to send. Oh, I could lie. If I'm a corrupted sender, I could lie. So maybe some people heard a 0, and some people heard a 1. However, if I'm honest, all the honest parties have what I wanted to send. They all have a 0, or they all have a 1. And in those cases, we should end up agreeing on that. I mean, if all the honest parties have a 0, we should of agreeing on 0. And if they all have a 1, we should agree on 1 because that's what I wanted to send. However, if the vote is mixed, if some honest party heard 0 and some honest party heard 1, then the sender is corrupted. And then there's no validity requirement. There's only the agreement requirement that they should end up deciding on the same all 0 or they all say 1. Does that remind you of something? Well, it's the definition of Byzantine agreement. So that's all they do. So they take these initial votes. Some heard 0, some heard 1. They run a Byzantine agreement to agree whether they all heard 0 or 1 and make sure that they always agree. And then they output that as the output of the broadcast. It's trivial. You just sit down and check that validity of the Byzantine agreements imply validity of the broadcast. Agreement implies agreement. Termination implies termination. That's all there is to it. Okay. And then that's it for showing the impossibility results. If we flip it up, but yeah, we also have a t strictly less than n30 here. Okay. So we know how to do broadcast and Byzantine agreement in the asynchronous setting with optimal bounds, both with signatures and without signatures. We were talking about asynchronous agreement, both broadcast and Byzantine agreement. We showed that you can do both asynchronous Byzantine agreement and broadcast if strictly less than n third parties are corrupted. We showed that that bound is optimal. Then maybe we also had an experience that the protocol that we needed for asynchronous Byzantine agreement was rather complicated. In particular, it used coin flipping. So what one can prove, there's a theorem which states that there is no deterministic asynchronous Byzantine agreement protocol tolerating a single crash silent error. Okay. By crash silent error, I mean that a server could crash and we don't like magically learn that it's crashed. When it's crashed, we don't learn it. The only thing we can observe in the system is that there will come no more messages from this server. And the root of the impossibility result then is that there is no way to distinguish that crash from an honest, perfectly operational server, which just have very slow messages. We call that we are in a model where messages might have arbitrary delay. Okay. We'll try to use that to prove impossibility of doing deterministic agreement. And the only budget we'll have to do with this will allow a single crash. Okay, so it's not Byzantine fault anymore. It's not 1/3. It's a single crash. Okay, so it's a very strong lower bound. It says that the problem we can solve with randomness when there's Byzantine errors, up to 1/3 Byzantine corruptions, we couldn't solve that without randomness, even if we just wanted to tolerate a single crash silent. Okay? So I would like to show now that we can't do asynchronous Byzantine agreement without randomness, without some party doing a random choice. The first thing I would like to show is that I can make a setting of the inputs of the parties such that when the protocol starts running, it's not determined what the output will be. Sometimes there's a one producing a 0, and sometimes there's one producing a run producing a 1. Okay, let's try to argue that. And this is the first place out of 2 where I use that I have a single corruption to do it. Okay, so let's have 0 here denote, let's say, no, let's have blue denote 0, and let's have brown here denote 1. Okay, let's look at a setting with 4 servers. This is server 1, server 2, server 3, server 4, and this is the output. Okay, so if we look at this one here, for example, it's a setting where servers 1, 2, and 3 have 0 as input. Server 4 has a 1 as input, and the output ended up being a 0. Okay. So there's a few things we know. Now I just filled this thing in. It's not given that in this setting we'll always agree on 0, right? And in this one it's a 1. But there are some things we do know about this figure here. I know that if all parties have input 0, the output has to be a 0. That is validity, right? So validity of Byzantine agreement says that if all honest parties have the same input, then they must agree on 0. So that I know. Up here, the output is always 0. Equivalently, down here, the output is always a 1. Okay? I want to show that there must be a line here where the output is not determined just by the input state, but where something non-deterministic can happen. The reason for that is there cannot be a single line here where you go from always 0 to always 1. So basically, this switch here can't be there anywhere. Okay? And if we start from somewhere where there's a blue here, blue means always output 0, and we end up in one where there's always output 1. And if in each line the output is determined, then there must be a first place where I switch from blue to red. Now I just put it here between lines 2 and 3, but I would have to put it somewhere, right? I can't keep putting blues because then it would just be down here it happens, right? So if the output was always determined only by the inputs, I can find a line like this. Blue here, brown there. Okay. And then I claim that can't be if I can tolerate a single corruption, because what I could do between these two lines, there's only one difference, namely pair 3 having input 0 or 1. But the first thing I could do with my budget of one crash silent corruption is to crash that party. So even before anyone gets to send a message, I kill party 3. Now, clearly, before this party had even the chance to tell anyone what its input was, I killed it. So the output can't depend on that input, right? We're now in a setting where there is input 0, crash party, input 1. Input 0, crash party, input 1. So it can't be that up here we always output a 0, and down here we always output a 1, because the settings are the same. Okay? So that was step 1. There must be some setting of inputs, probably a mixed one, or provably a mixed one, where the output is not determined by the inputs. So it looks like this. So let's say here, for example, when there's 2 zeros and 2 1s, it's not given on beforehand what the output will be. Sometimes it's blue, sometimes it's brown. How could that happen? How can we come from a situation where the output is undetermined to a situation where the output is determined? Because recall that when the protocol is done running, then of course all parties have the same output, 0 or 1. So at this point it's clear what the output is when we're done, right? So at the end the output is determined because it was already given. But we came from a situation, namely with these inputs here, where the output was not determined. So that's what these figures down here mean. So this is not longer the input, this is the output. And what kind of state is it in? In the beginning, it's in some kind of superposition between 0 and 1. It could go both ways. But at the end, it made a choice. It either become 0 or it either became a 1. So how could that happen? Well, there's a lot of non-determinism in our systems. Remember that messages can be arbitrarily delayed. So it could be, when this message comes first, the output becomes a 0. When this message becomes first, the output becomes a 1. So that could be one source of non-determinism, leading us from an undetermined state to a determined one. Could also be different crashes. Remember, we have a budget of one crash. And it could be that if party 2 crashes, the output is always a 0. And if party 1 crashes, the output is always a 1. It could also be randomness, even though we're now trying to think about whether we could do without it. But that would be another thing. It could be that at some point, like in swoop, some of the undetermined parties will flip a coin. That could also take us to either 0 or 1. And that's it. So in our model, that's all there is. There's an adversary that determines the scheduling. It can also crash. and then the parties could make randomness. And there's no other impact on the protocol. So given a sequence of when to deliver messages, when to corrupt them, and possibly what random choices people made, that completely determines the execution of the protocol. Okay? So it must be one of these sources of non-determinism, or a mix of them, that brings us from an undetermined state to a determined one. That's what I said. Oh no, here's a point to be made. It turns out that this impact from crashes, we can actually simulate that with scheduling of messages, by delaying messages. Namely, if crashing a party at some point would bring us into a state where we always end in a 0, I could have the same effect with just delaying all messages from that party from that point on indefinitely, or rather onto the point where the output is given. Okay, I just have all his messages or her messages arrive after people gave output. I'm allowed to do that. I'm only to guarantee eventual delivery, so I can just deliver them after the output was given. And that would of course have the same effect, because from the point of view of everyone else, whether I crash a party or forever delay its messages, they will do the same. They can't see whether the party is corrupt. They just see that they don't get messages. So let's forget crashing for now and just say, okay, so if there is such a protocol here that comes from an undetermined state to a determined one, there would also be one without crashes that have the same effect. It starts undetermined, and we can then bring it to either 0 or 1 just by scheduling. Okay. And then that leaves only 2 sources of non-determinism. So now we know that the way we get into a determined state is either by using scheduling of messages. I mean, I've sent this message before that one, or by using randomness. And since we're trying to do a proof of contradiction here, where we're actually trying to prove that we need randomness, let's do the following. Let's rule out randomness. So I'm going to say you're not allowed to use randomness, only scheduling. Okay? And you should use scheduling then to bring us from an undetermined state to a determined one. Then I prove that something impossible happens. And then we know that we made a false assumption along the line of thought, which must have been ruling out randomness as a source of impact, as a source of coming from an undetermined to a determined state. Okay. So for the sake of contradiction, I assume that the protocol is deterministic. So if the parties get the same inputs, they produce the same outputs. Okay, so now we have the following. I have a protocol which at the beginning is at an undetermined state. There is an execution of the protocol that will result in output 0. There's another execution that ends in output 1. And these 2 different outcomes can be achieved only by scheduling differently in which order some messages are delivered. Okay. Now let's try to reach our contradiction. Let's show that this will have some impossible effects. First of all, whenever I deliver a message to a party, let's say party 2 sent a message at some point and now I deliver it to party 7. That can have one of several effects. Let's say I'm in an undetermined state. It's clear if I'm in a determined state, if I'm in a state like this one, the blue one here, where the output is always 0, then in the next state, the output is also always 0, otherwise it would not always have been 0 here. So the second, this is the ball rolling to one of the sides in the soup, right? Right. So the figure will look like this here. So these figures are kind of showing what do we know about the output. If it's a full blue, we know that the output from now on will always be a 0, no matter how I schedule the remaining execution of the protocol. Brown means the output will always be 1, no matter how I schedule. And we know that we start from 1, where the output is undetermined. That means sometimes it's blue, sometimes it's brown, right? And then an error here, that means we map what is the effect of delivering a message. So this could be what's the effect of delivering message 2 right now. So in this case, it took us from an undetermined state to a state where the output is always 1. And it's also an end state. The protocol actually terminated, and we gave outputs. It could also be that by delivering message from party 3 to party 42, we come from an undetermined state to another undetermined one, where still both possible outputs are possible. We know a little bit about this figure. We know that if a state is undetermined, there must be a way to reach a fully read one, because we can produce final output 1. There's also an error to reach a fully blue one. Okay? And we also know that the end ones here, they are fully blue or fully red, because in the end state, parties gave outputs and there's no more messages to deliver. That allows us to find an interesting configuration, namely one of this form. There's an undetermined state in which if I deliver one message, we go into a brown state. And if I deliver another message, obviously, we go into a blue state. Why? Because I start in an undetermined one. And what I then do in each step in this graph here is I just keep going to another undetermined one if it's there. I keep following the longest possible path I can make of undetermined states. I know I run out of those before I end the leaf nodes, because in the end, the output is determined. Okay. Furthermore, I know that when I'm standing in the last undetermined state where I can no longer go to an undetermined state, one of the states I can go to is brown and the other one is blue. Okay. I know that everything I go to is either fully blue or fully brown, because there's no more undetermined states. Furthermore, since the state was undetermined, obviously there's a way to go to a blue one, and there's also a way to go to a brown one. Okay, so I can really find this exact configuration. Undetermined state, they can go directly to a fully brown or directly to a fully blue. By the way, we made this graph here. That means that there's some message I can deliver that fully resolves the protocol now. Boom, we know what the output will be. It will always be a 1. And another one I could deliver, and boom, the output is always 0. It's clear that these are two different messages, right? Because it cannot be that the same message have two different effects. It's really taking this exact message, delivering to this exact party at this point in time. Okay, so let's look at that thing. Okay, we identified that thing yet. I'm going to argue that it's impossible, that there can't be a state like this. But why is that? So what happens here? So there are these two messages that's delivered. Could it be that they're delivered to the same party or to different parties? Well, it's definitely one of those two cases, right? So let's try to go through both of them and show that both of them are impossible. So could it be that what happens here is that here I deliver a message to some party P, and to bring us in this state here of fully determined 0 output, I'm delivering some other message to another party Q. Could this be? No. And the reason is we are in an asynchronous system. So here's party P, here's party Q. There's a message that almost arrived here at party P, and there's another one almost arrived at party Q. Let's make those my thumbs. Now we're looking at a situation, a hypothetical situation, where if I deliver this message first, the output will always be a 0. If I deliver this message first, the output will always be a 1. And by agreement, this is of everyone in the system, right? But then if I deliver that one first and then right after that one, the output is always 0. But if I deliver that one first and that one right after, the output is always a 1. But since I'm in an asynchronous system, no matter whether I do like that, then that, or I do like that and then that, the state I end up in is exactly the same state. Parties don't know when they receive the message, so they cannot later compare nodes when got it first, because there is no clock. Parties do not have clocks. And when this party receives the message, no one else in the network can see it. If that was to be seen by someone else, this one would have to send a message first and have it delivered. But I don't do that. I deliver the message here, Then if that send outgoing messages, I just delay them for now, and then I deliver that one. I did my send out. Right? So I do like that, boom, like that, boom, and then I deliver these messages in the same order. Or I do like that one first, boom, that one first, boom, and then I deliver these messages in the same order. It's easy to see after a little bit of thought that the state I'm in is exactly the same, no matter who gets this message here first. I can do it milliseconds within each other, and they don't have a clock to see exactly when in physical time they got the message. So of course, I mean, if I'm in the same state after doing that, then that, or doing that, then that, then it can't be that it's in one state, the output will always be 0 and the other one always 1, because it's the same state. Okay. Okay. So, okay, that couldn't happen. That's a funny effect. So in a asynchronous system, you can't go from an undetermined state to determined one by delivering a message and have it kind of depend whether it came before or after another message in the system, because there's no way to compare when it happened. These are concurrent. If you remember our note on consistency, these messages are fully concurrent, and therefore they have the same effect on the system. Okay, so if it's not two messages delivered at two different parties, then it's two messages delivered at the same party. We know it's two messages because they have different effects. Okay. There's now a single party, and there's two messages coming to it. And then, I mean, I can either deliver this one first and then that one, or I could deliver the other way around. Right? That's what's going on here then. There are two messages where if I deliver one first, we always produce a 1 output in the system. And if I deliver the other one first, we always produce a 0 output in the system. So somehow P saw these messages in different orders and tells everyone what happened. And that's what determines what output we get. Except no, of course, because P cannot tell the other parties necessarily in which order these messages arrived. Why is that? I'm going to pause here for a second and let you think. Well, you can read it on the slide. It's because I could crash P, or rather, we're now in this imaginary setting where I'm only allowed to use scheduling. So what I could do is at P, I deliver one message first, and that will generate some outgoing messages. Or I deliver the other message first, and that will generate some other outgoing messages. But then I just delay them forever. I don't deliver these messages from P. I don't let it tell the world in which order it saw these two messages. And since the protocol we're looking at is one which could tolerate one crash error, right? Remember that we started with a protocol that can tolerate a crash error. I'm just doing without now, but the protocol could tolerate a crash error. That means that if P crashed at this point, all the other parties would still terminate. So what I do now with my scheduling is I delay the messages of P until everyone else terminated. Now, of course, since I don't hear from P, their output cannot depend on whether I delivered one message first to P or the other one first. So they will output the same, no matter which message of two incoming messages to P I deliver first. If I deliver them and then delay P forever using scheduling, the other parties will output the same thing. So that order of two messages at a single party cannot take us from an undetermined state to a determined state, because that party might not have time to tell the rest of the system what happened. So we rule out both cases. It's not two messages at different parties, it's not two messages at one party. And that's the contradiction. I mean, so there's no way this could have happened, this thing here. So the takeaway message here is then that a deterministic asynchronous system cannot be in an undetermined state from which it always transits into a determined state. That's really weird, but it's really this effect, right? That if that, if that affects somehow, I mean, that thing, if it always does that, it must happen somewhere. It's some message being delivered at a party. But one message being delivered at one party in an asynchronous system cannot have an effect on the system, really, because the next thing that happens is that the party could crash. And that's why these systems are so hard to program. And why in this particular case here, we see that we're forced into using randomness.